That's out of tune. Okay, welcome students. That's my musical introduction. So let's see. Let's take a look at this section is going to be kind of brief, where we are just looking at the three types of discontinuity. So we talked about what continuity is and what it means for a function to be discontinuous at a point. Well, we classify this way. So anytime that you have just a bubble, and you don't really have to have that dot there, you just have the bubble, the left and right hand limit are coming together at the same point, we call that a removable discontinuity. A jump discontinuity is when there's a jump and the left and right hand limit are not equal. So I think it's good to kind of write down a little note to yourself on each thing here. So this one, really what happens is the limit as x approaches a of f of x, it exists. Okay, so that limit does exist, but what happens on this is that limit is not equal to the function value. So it kind of works like this. The limit f of x as x approaches a is not equal to f of a. And really that condition doesn't matter. It's just the limit does exist, and then you're not defined there, okay, at that point. So the next thing is what we call a jump discontinuity. And what this is we say the limit as x approaches a from the left, f of x equals some number L. And then we could say the limit as x approaches a from the right is some number m, and they're different. Okay, so L and m are not the same. Okay. All right, and that's how that goes. Now, the other type of discontinuity is an infinite discontinuity. And what this will always happen if the limit as x approaches a from the left of f of x and the limit of f of x as x approaches a from the right, if they go to either plus or minus infinity. So what that means is if your left and right hand limit go to either plus or minus infinity, it just means you have a vertical asymptote. So that's kind of the idea behind that. That's what each situation lends itself to as far as the limit goes. Okay, so removable limit exists. Jump discontinuity, left and right limit exist, but they're different. The values are different. Infinite discontinuity, the left and right both go to plus or minus infinity. So that's how that works. So summarized on the next page of your handout is what I just talked about. It has a removable discontinuity, which typically just kind of looks like that. It may or may not have that bubble up, that solid dot like there. That the limit exists as x approaches a, is you're going to have a removable discontinuity, right? And then what happens on the second one, you have a jump discontinuity, which would look something like this. Okay, that's just the left and right hand limit exists, but they are not equal. That's what I just showed you on the previous page. Okay, and then the infinite discontinuity is where you have a asymptote, and the left and right hand limit either go to plus or minus infinity. So that's how you can locate the type of discontinuity based on the definition without looking at the graph. So what I'm going to do with these examples is we're going to identify the type of discontinuity, and then we can verify it on the graphing calculator. Okay, so if you look at these definitions, it's all about limits. We need to see if the limit exists or the limit doesn't exist. That's kind of it. And I think there's this will be summarized. This is kind of a good thing. If I'm going to jump down here for a minute, and I'm going to take a little screenshot of this. I wish I would have put this a little bit higher up in the notes, but this is sort of a flow chart that you can go through to reason this out. So I'm going to just paste this over here and refer to that as I work some of this out. So if you're going to figure this out, you can kind of follow this flow chart. So the step one is just let's see if the limit exists or not. So we're going to go ahead on this, and we're going to do the limit as x approaches -4 of x plus 4 over x the second minus 16 And we'll see if it exists or not. Well, if we plug this in on this, we would have negative 4 over negative 4 squared minus 16. So if you work that out, that is 0 over 0. Now remember, if it's 0 over 0, we know the limit exists. Okay? So we need to go ahead and we need to figure it out. We need to figure out that limit. So yeah, that would be a yes. We're now to this step. We need to see if the limit of f of x is equal to f of c. So if we go ahead and do the limit, we're going to have to factor. So we have x plus 4 over x plus 4 times x minus 4. That's the difference of two squares. Okay, and then that will cross that out. And then what we need to do is this. We need to look at what we're left with. So we're left with the limit as x approaches negative 4 of 1 over x minus 4. So that would be 1 over negative 4 minus 4. So that is just a negative 1/8 like that. Okay, so the function value, so what happens on this then is it's kind of like this. What would happen on this is the limit does exist as x approaches a. Now, what's the value of the function? So you also have to kind of look at, well, what is f of negative 4? If we do f of negative 4, well, we got something that's undefined. We already did that, so we got 0 over 0, so they're not different. Okay, so basically what happens here is the value of the limit is not the same as the value of the function. The function's undefined at negative 4, so on this flow chart, that means you're here. So we kind of did this. The limit existed, yes, but the limit was not the same as the function value. Therefore, what we conclude on this one is this is a removable discontinuity. Okay, that's how that goes. It's just the limit. We're trying to see if the limit exists. If it does, see if it's the same as the function value. If it was the same, then it would be continuous. It would basically satisfy all the conditions of continuity. Okay. Now, you can close off a problem like this by doing this on your graphing calculator. And you can do this with me, or you can just watch. I'm just going to put in the original problem. I've got rational function x plus 4 in the numerator. And then I've got x squared minus 4 in the denominator like that. I'll just do standard window. And remember, we're looking at the discontinuity at negative 4. So we have removable. Well, okay, if you look at this, here's negative 4. Okay, you can tell the limit exists. The left and right-hand limit are both going to the same place. In fact, the value of the limit's negative 1/8 if you do that. So, but what happens on this, the function's undefined there. So if you traced it negative 4, well, there would actually be an open bubble there. So that would be what we would expect from a removable discontinuity. The limit exists, left and right go to the same place, but the function's undefined. And the value of that limit, therefore, is not the same as the function value. So that verifies that that's a removable discontinuity. Okay. Okay, let's try this next one here, and we'll just kind of continue to follow this flow chart. Okay, so let's see. Next thing we do here is, again, we're going to see if the limit exists at this point or not. Well, this is a piecewise function, so really all you can do on this is you can just kind of look at the left and right-hand limit on this, okay? And so step one would be, let's just look at the limit of g of x. Oops, not that way. Come on, teacher. Limit of g of x as x approaches 1. Okay. So what we need to do on this is, well, it's in two pieces. So we're going to do like a left-hand limit. Whoops, hold on. I'm doing that backwards. So we're going to do a right-hand limit here. Since that is x is greater than 1, we're going to do right-hand limit. And then we're going to do a left-hand limit there. Okay, so it's piecewise function, so we need to really just kind of consider what's going on the left and right-hand limit. We have to do it that way. So let's see, if we do the limit of the function 2 as x approaches 1 from the right-hand side, well, that's equal to 2. It's a constant, so it has to be equal to 2. And then we have to do this. We have to do the limit as x approaches 1 from the left-hand side, since that's less than or equal to 1 of -2, that's -2. Okay, so you tell me, what happens to the limit? Is the two-sided limit going to exist? Okay, no. Okay, so therefore, those little three dots are kind of my therefore. Okay, so we'd say, therefore, the limit of g of x as x approaches 1, the two-sided limit does not exist. Okay, so we're here. Okay, so that's where we are in our checklist, is we're over here. So the next question is, do the one-sided limits exist but are unequal? Yeah, that's what we just found. Okay, we just showed they're unequal. So therefore, this one is a jump discontinuity. Okay, that's how you do it. Right, now, if you were to consider the graph on this, you don't want to waste your time really doing this on the graphing calculator. What would happen on this problem is we're interested at x equals 1, and we have 2 and -2. I'll show you exactly how the graph goes, and you want to know how to be able to do this pretty easily. When x is greater than 1, that's this way, the function is 2. And then this says if x is less than or equal to 1, the function takes on the value of -2. So you can tell by that graph that that's clearly a jump discontinuity. Okay, but that's how the mathematics works. The limit did not exist, and the one-sided limits exist, but they're unequal. That's why it's a jump. Okay. Okay. So I like this flow chart. This is a good way to kind of summarize these definitions up here. Okay, so we'll go down to this one. Step one is always just, does the limit exist? So this one we're going to go ahead and do the limit as x goes to 4 of x plus 4 over x the second minus 16. Okay, well, let's just go ahead and factor and kind of see what happens on this. So we have the limit as x goes to 4 of x plus 4 over x plus 4x minus 4. So that is the difference of two squares. Okay, and we'll do this then. All right, so what's going to happen here is that's going to cancel out. So now if we do the limit, now we're going to do the limit x goes to 4 of 1 over x minus 4. Well, we got a problem here. If you plug that in, you get 1 over 0, so you're undefined. So what happens on this, and one of the things I think we talked about a little bit, this part right here is the whole. We talked about if you have a rational function, the factor that cancels out is the whole. So you have a whole at x equals -4. The one that's left over is a vertical asymptote. So you have a vertical asymptote at x equals 4, and that really is what makes it an infinite discontinuity. So what happens is the limit doesn't exist. Okay, so we're really down there. The limit right here, we got that. The limit doesn't exist. Okay, and then what happens on this is, do the one-side limits exist? But are unequal. Well, what happens on this is when you get into the infinite part of this. What you would find on this, and this is kind of what I taught you how to do, you know you have a vertical asymptote. You know that for a fact. So what you do is, if you're going to do the limit as x approaches 4 from the left-hand side, you could use test points. And then if you were doing the limit as x approached 4 from the right-hand side, again, you could just do test points. So what would happen here is this would be the limit of 1 over x minus 4. Okay, there's a left-hand limit, so we could use, like, say, 3.9. So if we did 1 over 3.9 minus 4, we get a positive over a negative. We get a negative number. So therefore, that left-hand limit's going to negative infinity. All right. And then the same thing would happen on the right-hand limit if we used like 4.1 and plugged it into that function. We'd have 1 over 4.1 minus 4. That's positive over positive, so it's positive. So therefore, that would approach the infinity. And if you look at the definition up here, an infinite discontinuity occurs where the left and right-hand limit are both going to negative or positive infinity. Okay, so that's kind of the idea on this one. So this one would be an infinite discontinuity. Okay, so that's how you piece that thing together then. That's how you figure out, mathematically speaking, how these graphs go. If you graph that on the calculator, and that's really the same as the one that I had for number 1. So if you look at this problem, if x equals 4, 1, 2, 3, is that the same problem? Oh, that's supposed to be a 16. Okay, I have to put that in my calculator wrong. Okay, yeah, now we're good. Okay, so if x equals 4, you have a vertical asymptote. Left and right hand limits go to infinity, so plus or minus infinity, so you have a infinite discontinuity. Okay. Okay, so I wanted to kind of show you how you do that. That's how you classify the types of continuity without graphing. Graphing makes it easy, of course, but trying to get these definitions down, this is the way you'd want to do this. Okay, so I think I'm ready for you to do a few problems here. So pause if you need to look over what I did there. And again, I'm just sort of following the flow chart. Kind of the key thing on here, when you get an infinite discontinuity, is it's just basically the left and right hand limits are going towards infinity. That's probably a better thing to write on here. Do the one side of the limits exist but are unequal? Yes, it's a jump discontinuity. They exist in their infinity. This is probably a good way to just think of this part right here is the limits go to plus or minus infinity. Okay, so let's see, go ahead and pause and let's do these two. Let you work on these a little bit. I'm giving you a graph. You tell me where it's discontinuous and you tell me what the type is, which is removable, jump, or infinite. Good luck. Okay, check and see if you got what I got. So these are the places you have discontinuities. You got -2, -1/2, 0, 1, 3, and 5. So the removable, the -2 is removable. Again, the limit exists, but it's not equal to the value of the function. And the function doesn't even exist. At -1/2, I estimated, it looks like the limit exists, but the value of that limit seems to be 3.5. The function value is 1. Okay, and it's easy to identify these things visually, but think about the technical definition. The higher you get in math, the more technical it gets, and the more you gotta make sure you understand definitions well. Okay, all right. So let's see. 0 was jump. That's because the limit does not exist. And let's see, the second at 1, that's jump. Again, the left and right hand limits, they exist, but they're unequal. And then 3 is infinite. Okay, the limit, left and right hand limit both go to infinity, plus or minus infinity. And then at finally at 5, that's removable. On removable, the limit exists, but the value of the limit is not the same as the function value. All right, so let's move to the next thing here. So what we're going to do here on this one is we're going to apply the definition of continuity at a specific value of x, and we're going to classify the discontinuity of each function. So I want you to use the flow chart on this one. I want you to go ahead and pause the video and do this. Now, before you check the answers and resume the video, it's not a bad idea to check on a graphing calculator and see if you're correct. But try to just apply that flow chart. I'm going to make a copy of that flow chart and put it right here. Okay, go for it. See how you do. Okay, so I left part C blank because I didn't even tell you what place I wanted you to do. You may have assumed that it was x equals 2. That's what I was intending. That one I wanted to show you something on anyway because of the absolute value. So let's at least check these two. This is the same function, but we're looking at x equals 1, x equals 0. And again, we can kind of look at the flow chart on here. The first thing is always just do the limit and see if it exists. So basically on this one, I'll tell you how you can get to your answer real quick on this one, is if you go ahead and plug the 1 in, you would have 1 over 1 to the second minus 1. It's 1 over 0. That's not a 0 over 0 form of a limit. Okay, remember, it's 0 over 0, it exists, so you'd have to move on. Well, this is going to end up having a vertical asymptote. And if you conclude that it has a vertical asymptote, that's all you got to do to tell it's an infinite discontinuity. So I went ahead and factored the x out of the bottom. So I have x over x times x minus 1. That cancels. And remember, the one that cancels is the whole. So we know we have a whole at x equals 0. We're left over with 1 over x minus 1. So you're undefined. So you have a vertical asymptote at x equals 1. Problem done. Okay, if you have a vertical asymptote, it's an infinite discontinuity. You don't have to do anything else. Okay, so that's it. Okay, you can even bypass the limit on this thing if you want to. You could just do exactly what we learned here. This is x over x times x minus 1, whole at x equals 0. Vertical asymptote at x equals 1. And again, we're looking at the limit at x equals 1. Therefore, it's infinite. That's it. Boom, boom. Problem done. Okay. Next one, we're just doing the same thing, but x goes to 0. Okay, well, if you do this one, what would happen is, again, same idea, x's cancel out. So reevaluate the limit as x goes to 0 of 1 over x minus 1. Plug the 0 in, you have 1 over negative 1. So the value of that limit does exist. Okay, then what we got to do is see what the value of the function is. Okay, well, if you look at this function, if you plug a 0 in at the beginning, this function's undefined because you end up with a 0 denominator, so it's undefined. So these things are different. That's kind of what you're checking here. So the limit exists, the value of the limit's -1, but the function's undefined, so therefore this statement here does not hold, so therefore it's removable. So that's how you would come up with that. And if you look at, this is the graph, I put this on the calculator right here, you can see the infinite is at 1. Removables here, there's a hole. So we figure out that there's a hole. I think I put the hole in the wrong place. The hole is at 0. So that's a removable discontinuity. Okay. So this one on the absolute value, let me kind of talk through what you have to do on this. You know, if you start immediately on this, you run into some problems on doing limits with absolute value functions without applying the definition of absolute value. So one thing I recommend on here is just do the left and right hand limit. Obviously, if you plugged in, if you did f of 2, you would just get absolute value of 2 minus 2 over 2 minus 2. So you would get 0 over 0. So you do have that 0 over 0 limit, so we know the value of that limit exists. Okay. I'm going to do this without doing the definition. I think you'll probably understand this a little bit better. We're going to do it with test points. I need to kind of get a little bit of room here. So what I'm going to do is I'm going to do this. Okay, you have a place where you have a 0 denominator, so you actually have a vertical you don't have a vertical asymptote on this. Something a little bit different happens. So we're going to do the limit as x approaches 2 from the left-hand side of this function. And we're going to do this just with test points. So just take a number that's just a little bit smaller than 2, say like 1.9. So you'd have absolute value 1.9 minus 2 over 1.9 minus 2 like that. Okay, well, let's see. That would end up giving the same thing. Now, what's important is the numerator is positive, the denominator is negative. And aren't they the same? I mean, if you think about this, then you're doing the same math problem. You're doing 1.9 minus 2 over 1.9 minus 2. So they're going to end up canceling out, but you have a positive over a negative, so you have a negative. Okay, so that's going like that. So you have some sort of a negative result when you do that then. And if you went ahead and did that, you would actually get -1, because this would just end up really being the absolute value of -0.1 and the denominator would be negative 0.1, so you would have negative 1. So that's what the value of that limit is. That's negative 1. Okay, and then if you do the right-hand side, as x approaches 2 from the right, you're going to do the same thing. We're just going to use a test point. Okay, use like 2.1. Okay, plug in, you're going to have absolute value 2.1 minus 2 over 2.1 minus 2. The numerator is going to be a positive 0.1. The denominator is also positive 0.1, so therefore that equals 1. So you're going to end up having the left-hand limit going here, the right-hand limit going there. All right, so what's going to happen? If the left and right-hand limit go to different places, then the two-sided limit does not exist on that. And then what will happen with this is, so if you look at the flow chart we're doing, it would kind of go like this. So does the limit exist on this one? Well, no, it doesn't exist because the left and right go to different numbers on that. And then with this one, do the one-sided limits exist? Yes. But they're unequal? Yeah, they're unequal, so that's a jump discontinuity. Okay, so that's what that would be. Now, there was one little thing on here I kind of caught when I was teaching this, and maybe some of you did too. I've kind of told you that 0 over 0 will typically, I think I may have erroneously said a few times that it'll exist, the limit exists as guaranteed. That's not necessarily true. It typically exists, so I guess in most cases that you run across, it's going to exist. But in this case, even though you have a 0 over 0 form of the limit, it doesn't exist because the left and right-hand limits go to different places. So this is kind of one of the more atypical results that you get. Okay, so let's see. I'm going to do just one other little thing. I'm going to work a few little extra examples out on here and then kind of get this part of the video in the books here. So on this function, we're just going to identify where the function's discontinuous. Okay, so we got to know something about functions on these. And in Calc 1, there's all kinds of functions that you looked at in trig and college algebra and so forth. Well, first of all, the thing on this is a rational function. So it's all about where is the denominator 0. That's what the question is. If you can figure that out, if it's undefined, remember, if the function's undefined, it's discontinuous there. So what I'm going to do is factor the denominator. So I've got f of t is t plus 3. And over here I've got the factor of the denominator. You're going to have t plus 3 times t plus 2. All right. So this thing is undefined at two places. It's undefined at t equals negative 3 and at t equals negative 2. So therefore, we would say we're discontinuous at negative 3 and 2. Okay, now notice I didn't worry about the cancellation there. Sometimes students will cancel that out, and then they will think that it's only discontinuous at negative 2. But it isn't. It's discontinuous at negative 3. Remember what we learned? This is a hole. Okay, hole at negative 3, vertical asymptote at negative 2. So we've seen that situation show up several times. When you have a hole, it's a removable discontinuity. When you have a vertical asymptote, it's a imminent discontinuity. So that's how it works out. Okay, well, look at this next problem. It's the same idea. Okay, you have a fraction. So the question is, where is the denominator equal to 0? So we're going to just write an equation. E to the x minus 10 equals 0. Now you got to dig into your background and see if you remember how to solve an exponential equation. So we're going to move the 10 over here to get e to the x equals 10. We're going to do natural log of both sides. This is stuff you may have to brush up on a little bit. Depends on how well you did with pre-calc or college algebra. Okay, the rule of logarithms is you can bring that down. So that's x times ln of v is equal to ln of 10. And then the ln of v is equal to 1. That'll pop up all the time, so you want to know what that is. If you ever forget, well, you can figure it out. If you know what a logarithm is, you can figure anything out on logarithms. So this is logarithm base e of e equals 1. And the reason this is right is because e to the first is equal to e. If you write that in exponential form, then you get 1. So that part becomes 1, so you end up getting x is equal to ln 10. So we are undefined there. So the answer to this problem would be we are discontinuous at x equals ln of 10. Okay, that's it. And you want to just leave it like that. Okay, let's take a look. I think it's always good, if you're in doubt, if you're ever in doubt about what the mathematics is doing, just look at your calculator and look how the graph goes. So if you put this in, you would have 10 over, and then you would have e to the x, and then minus 10, like that. Okay, then you're going to do then just do a basic graph. All right, so let's just graph it, standard window. Look what happens. Okay, well, we got an asymptote. We have a vertical asymptote, so we do have an infinite discontinuity at ln 10. The other thing you can do to verify that, if you trace ln 10, well, you're undefined. Okay, that's where that is. That is happening right there. And see, that's at ln 10 is about 2.3. So notice if you're about 2.3, you can tell that's where that asymptote is. Okay, and you can make notes of yourself on this if you're as you're going through the video. If you want to go through and do make a little note of the graph, you always can. You can sketch a graph if you want to, but you don't have to. So those two problems were done the same way. The thought process is the function is a fraction. And if I have a fraction, I need to know what makes the denominator equal to 0. If I can figure out where the denominator is 0, then I automatically know where it's discontinuous. Okay. Right, now you're going to deal a little bit with trig. So let me show you what happens on trig. We're going to kind of do a little review on this, and we're trying to figure out where the tangent is undefined. So what I'm going to do on this, I'm going to pause and I'm going to bring up a unit circle. So just as soon as you won't see the. Okay, so like magic, there's my unit circle. That actually looks like a unit oval. So let me fix that. That's a little better. Okay, now we got a unit circle. Okay, so let's say that you don't remember a thing about what the graph of the tangent looks like. If you do, it's helpful because the graph of the tangent has a bunch of vertical asymptotes. So this is going to have infinite discontinuities, an infinite number of them actually, because the tangent graph we're going to look at all the way from negative infinity to infinity, so it technically has an infinite number of vertical asymptotes. What you do want to remember is the definition of the tangent of an angle theta is y over x. And I always say the unit circle's God. It's the God of trigonometry. All of the answers to trigonometry are in this diagram right here. So what we're going to do is we're going to figure out where is the tangent undefined. So ultimately that means you got to look at y over x on the unit circle. So ultimately you got to figure out, well, where is x equal to 0? The question ultimately becomes, where is x 0? Where x is 0, that is where the tangent is undefined, where it has a vertical asymptote. All right, so look, tell me where is x equals 0? Okay, there and there. That happens at two places in radians. That happens at pi over 2 and 3 pi over 2 like that. Okay, now what we have to do is we know that we're undefined at pi over 2 and 3 pi over 2. However, these asymptotes go on forever. So if I want you to tell me where it's discontinuous, well, then you would have to write a formula. You couldn't just list out of these infinite number of places. Well, there's a pattern to that. Okay, so basically if you do this, you got pi over 2, then you got 3 pi over 2, but then you can go like this. You can go from there, and then you can go all the way back there again. So every time that you go through pi radians, you're at another place on the same place on the unit circle. So this has a pattern to it. 1 pi over 2, 3 pi over 2. What do you predict comes after 1 pi, 3 pi, 5 pi? There we go. 5 pi, 7 pi over 2. Odd pi over 2 is where the tangent's undefined. Okay, you figure that out from the unit circle. It's just very clear. If you know that the tangent's y over x, then the tangent's undefined where x is 0. And then you can just kind of count off those angles. Now this has a pattern to it, and just kind of depends on what you did in trig or pre-calc. I like to have students write down formulas, so you write this down as like this. This is what's changing. 1, 3, 5, 7, 9 is changing. Pi over 2 is always there. Like I said in words, I said you have an odd pi over 2. Odd pi over 2. So you write this as k pi over 2, where k, and what is k? K is an odd integer. Now remember, integers have negative numbers also, so you also could have negative pi over 2. See, this goes this way too. Negative pi over 2, negative 3 pi over 2. It keeps going that way too, see? Okay, so what on this one we would say is discontinuous at x equals k pi over 2, where k is, and you have to write that out. You have to put the odd integer or you're not correct. You're not telling me what I need to know. I need to hear this. So you're discontinuous there. And there's an infinite number of places where the graph of the tangent's discontinuous. All right, let me just kind of remind you of a couple things here. Graphing calculator, great tool. It'll kind of open everything up. If you were going to graph the tangent, the first thing you'd want to do is the mode would have to be radian. So I go mode and make sure that's in radian mode. If you happen to be in degree mode, you just need to bring it over, press enter, and then you're good. For a window, I'm going to do this. I'm going to go negative 2 pi to 2 pi, and probably scale that by pi over 2. And for the y's, let's just do negative 10 to 10. Okay, and let's just see if this looks familiar to you. So if we put in y equals tangent x, see if this is what you were taught. See, there's an infinite number of asymptotes. One of them is pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so forth. Odd pi over 2. That's where that happens, okay? So that's how you do that. Okay, it seems like it's getting a little sloppy on this then, so we got that. So the next problem, okay, the first thing I would consider is that's a negative exponent. How do you make a negative exponent positive? Well, you write it that way. That's what you've learned in the past. Okay, now the question is, okay, your thought process as student. Oh, teacher gave me fraction. Teacher gave me fraction. Where is fraction undefined? Okay, that occurs wherever the denominator is 0. So the question that you ask in your mind is, where is the denominator equal to 0? You do that in your head. That happens when t is 0. So we would say discontinuous at t equals 0. And that's it. Okay, that's how you would want to do that. Problem is kind of like that. Okay, all right. But remember, what I showed you in these problems is the same idea. What you're trying to do is get more and more and more comfortable with functions when you're studying calculus. So the first two gave you fractions. Teacher gave you fractions. What's the thought process? Okay, where is the denominator 0? Part D, same thing. Teacher gave you fraction in disguise. T is negative 2. 1 over t squared. Okay, t equals 0 is where you're undefined. Trig functions are kind of interesting. You have to, if you learn your trig function graphs well, you're going to find that the tangent, cotangent, secant, and cosecant all have vertical asymptotes. The sine and cosine don't have any asymptotes. Okay, so the discontinuity on the secant, cosecant, cotangent, and tangent is all dependent on whether you can figure out what those vertical asymptotes are and whether you can write a formula for it. Right? So that's the idea. All right. So let's see. We're gonna finish this up here. So all I'm gonna do to finish up the video on here is have you go to the next page, do these problems. I'll provide you a unit circle. I think I gave cosecant So we want to figure out where the cosecant is discontinuous. So go ahead and pause and see if you can get these figured out. Okay, so I'll close this off. You can see what you came up with. So with this first one, I gave you a fraction. So the same idea. Teacher gives fraction. Student says, I need to figure out where denominator is 0. And this one you can do in your head. So the idea on this is if x is -1, then you have a 0 denominator. So this is discontinuous at x equals -1. That's the only place where that function's undefined. Okay. Same thing with this one. Now you have to factor. Okay. Sometimes students have a little trouble in Calc 1 with some of the factoring, particularly this part. So you should have factored it like this. So there's 2 places. Don't worry about the 2x plus 3 canceling. That just means there's a hole in the graph. Still means you're discontinuous. So you do solve the equation 2x plus 3 is 0, which gives -3/2. And then x minus 5 equals 0 is 5. So those are the 2 locations where you're discontinuous. That's dependent on how well you can factor. Okay, now remember what I said is it's the cosecant, the secant, the tangent, and the cotangent. They have vertical asymptotes. So they're going to be discontinuous wherever the vertical asymptote exists. So the only way to figure this out without doing a calculator or anything like that is you got to know the unit circle, which is the trig god, and then you got to know your definition. So the cosecant's r over y. Okay, so it's r over y. So the question is, okay, what makes y 0? We can't have a 0 denominator. So where is y 0? Here and here. That's at 0 radians and pi radians. And then you got to remember how you learned about this in trig or pre-calc. It's pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. All kinds of things sometimes students never catch, but this is just over here. This is 0 pi, 2 pi, 4 pi. So I think of it as even pi. Over here, this is 1 pi, 3 pi, 5 pi. So I think of that as odd pi. Okay, so that's how that goes. So this is at every pi. All right, so every time you hit a pi, then y is 0. Okay, on a unit circle. So we would say it's discontinuous at x equals k pi, and k is an integer. Remember, integers are 1, 2, 3, 0, -1, -2, and so forth like that. Okay, so that's how you figure that out. On a graphing calculator, by the way, it goes like this. The way to graph the cosecant is the cosecant you learned is 1 over sine. So I just put in 1 over sine and look at the asymptotes. Now the way I've got this, like if I trace it pi, if I put trace pi, okay, well, it's undefined. That's where pi is right there. Here's where 2 pi is. So I've got the graph is going pi over 2, pi, 3 pi over 2, 2 pi. So all of the integer pi's is where you have an asymptote. So that all comes from the unit circle. You get higher in calc, you go like to calc 2, and you got to figure out asymptotes in your head on these trig functions like real fast. Okay, and you just need to know the unit circle and know the definitions. Okay, so this last one here, what I hope that you did is you just rewrote it as 1 over x squared plus 1 to the first. So it's like this. We're really looking at that function there. So then the thought process is, okay, I have a fraction. I got to figure out where's the denominator 0, so I have to solve this equation. Okay, and you can do this in your head. If you take any number and square it and add 1 to it, you'll never get 0. So this one is nowhere discontinuous. If you didn't see that, you could try to solve this equation. You could subtract 1 from both sides, square root, well, you get an imaginary number, see. So it's nowhere discontinuous. And again, you know what I want you to kind of do, like when you're doing your homework and stuff like this, you want to try to do as independently of touching your calculator as you can possibly be. You get in higher math, you're going to do stuff on the fly all the time, just in your head, mentally. Figure stuff out, reason stuff out. So if you did put this in, even in the original form, if you put parentheses x squared plus 1, close parentheses to the -1, and do a standard graph on this, there isn't any breaks. There's no breaks to be found, so it's continuous everywhere. That's the idea. Okay, so that'll kind of wrap that up. my ending on my stupid thing. Okay, we'll have a guitar next time. All right. Good luck.